I left my laptop on a tram this morning, so I'm sorry about the delay. So yeah, I'm Tong, and I work at the electric coin company. And today I'm going to tell you about UltraPLONK arithmetisation. So this is a way to represent a statement or a relation as a series of polynomial constraints using PLONK and using custom gates. Since coming to Devconnect, I've actually learned about a whole series of PLONKish arithmetisation efforts that are like UltraPLONK. And so at 4 a.m. today, I decided that I want to talk about them as well. I want to mention them. And I want to talk about UltraPLONK, not just in its current state, but also in terms of its open problems and its future developments. So the standard PLONK gate is basically what you see here. It's one constraint with different selectors that you can tweak. So if you set the selectors to certain values, you get certain types of expressions. So this is an addition gate, for example, and you can have a multiplication gate as well. So UltraPLONK basically generalizes this idea to let you define custom gates that are arbitrary expressions. And we simply combine different custom gates with a random linear factor to keep them linearly independent. And then so on each row of the circuit, you can choose to enable or disable whichever gates you want. So one area of development that we're thinking about is to actually have this randomness be an in-circuit feature. So this is an idea by Han. I don't know if it's here, but for example, we can allow the prover to first commit to certain witnessed values, and then using those commitments derive some randomness to then use in the expressions themselves. And in general, the mental model of PLONKish arithmetisation is a matrix of rows and columns. So each value in the matrix is a field element from a certain finite field. Can I get rid of this? Sorry about that. Now, what do the rows and columns represent in this matrix? Each column maps to a polynomial, a Lagrange interpolation polynomial, that interpolates to that value assigned at the cell when evaluated at the point omega to the I. So omega here is the primitive nth root of unity in your evaluation domain. And yeah, so each column evaluates to the cell fxij when evaluated at omega to the I. We have different types of columns in this table. So instance columns are basically those contain values that are shared between the prover and the verifier. So for example, your public inputs will be provided in the instance columns. Advised columns are where the prover witnesses their private inputs. And the instance columns and advised columns change from one proof instance to the next. And yeah, they're basically what's unique about your proof instance. Whereas the fixed columns are a different beast altogether. They're pre-processed values, and they're computed at key generation time by the verifier. And these are hard-coded. They define your circuit, and they never change from one proof instance to the next. So here's an example of a custom gate. So let's say we have an addition gate QAdd that checks that that the cell in A2 is the sum of the cells in A0 and A1. So on the rows where we enable it, we check that this constraint evaluates to 0. Now, the thing about custom gates is that they can have an arbitrary shape. So you're able to access values in other rows, and you're able to specify an arbitrary offset by which you're rotating your row. So if you have a certain shape of gate that's more efficient for your circuit, then this is a good chance for you to express that. And how we achieve these relative offsets is by making use of the fact that our evaluation domain is over the powers of the primitive nth root of unity. And we can simply rotate by multiplying by powers of omega. So from here, we have basically the idea of the custom gate as a template, like as a Tetris piece. And what we eventually want to do is have some kind of macro that describes a gate. And if we input into it our configuration, so the number of columns and number of rows that we have, and we input into it some expression that we want the gate to check, we should get out of this macro the optimal gate shape, basically. Right now, we don't have a macro like that, and everything is manual, and the developer has full freedom. But if we could write some kind of compiler that's smart enough to figure out a gate shape, that would save us a lot of effort. At Devconnect, I've learned about a few efforts like this. For instance, the vampire intermediate representation, and also MENA protocol's kimchi. So we're definitely interested in basically converging on a standard intermediate representation, hopefully. So if we think about laying out the circuit, it's really a question of optimizing the global use of space. But at the same time, our gates are very local in nature. We're reasoning about offsets relative to the point at which the gate is enabled. So how do we reconcile these two scopes? The ECC implementation has this abstraction, the region, that aims to serve as a boundary between the global layout and the local gate. So each region is basically a self-consistent block, and each region is defined by the fact that it uses the same global offset. And what this means is that one region is not affected by another, and we can move regions around without affecting their internal gate logic. And this gives us a lot of freedom for optimization. So, for example, our layouter can be authorized to compress regions. This layouter on your right basically slides regions up vertically, and you can see the huge efficiency gain we have. We basically have reduced our row usage by half. Yeah. And a further layouter optimization that we want is basically just horizontal packing as well. We don't have it currently because that would require the layouter to be able to change the configuration. So you have to authorize your layouter to like reduce the number of columns you have, for example. And right now the layouter doesn't do that yet, but it would be cool. Oh, yes, definitely. The colors, so the pink colors, the pink columns are advised columns. The light purple columns are fixed columns, and the dark purple columns are what we call selectors, which are basically just a special case of fixed columns. They are binary fixed columns, yeah. I've tried to stick to this color scheme in like here as well. So it's consistent. Yep. So besides custom gates, we have another tool, which is the equality constraint. So these are global constraints that enforce the equality of one cell with another cell. So this is the orchard action circuit. We have a lot of equality constraints, but yeah, basically it's just made up of a series of permutations like these, and we form a global permutation. It's a huge cycle, or many cycles. Yeah. And equality constraints allow us to link regions together. Even after you move them around, you can still apply a global constraint that basically lets you copy a value from one region to another, and that's highly useful. The final tool that we have is a lookup argument, and you can think of this as like a special case of an equality constraint that doesn't enforce a specific permutation, rather it enforces just a subset check. So over here, QLOOKUP is saying that these two values in A0 and A1 must be a subset of this table, the Fibonacci numbers. Yeah. And it's perhaps a kind of a technical note over here, but for a lookup argument must hold true on every row. So on the rows where QLOOKUP equals 1, these values must be a subset of the table. But on the rows where QLOOKUP equals 0, then these two expressions would go to 0, 0 by default, right? And if your table does not have the row 0, 0 in it, your lookup argument will fail. So when you're writing a lookup argument, you have to think about the default case. And that's what I've done here. I've put in a 1 minus QLOOKUP. So when QLOOKUP is 0, we check this constraint. And I've put in the default 1, 1 value that basically will allow the lookup argument to pass on every row. Yeah. So, and if you want to learn more about this stuff at this level of detail, you can come to our workshop, me and Chichung's workshop in the afternoon. Yeah, what we want from lookup tables that we don't have yet is the ability to make them dynamic, to look up values that the prover has witnessed. So right now, the Zcash Halo 2 supports only fixed table columns, and this is a safety and API concern. We basically want to be able to pad the lookup table for you with default values. But there are many use cases that require more flexibility and that require looking up values that change from one proof instance to the other. So yeah, we're definitely thinking about this, and we're brainstorming some APIs that make dynamic lookups safe. So those are pretty much all the tools you have in PLONKish arithmetisation. And using these tools, we've built, many interesting circuits. So for example, the Poseidon hash, the Synthamia hash, which is our own in-house hash. We've built gadgets for elliptic curve cryptography and an experimental SHA-256 gadget. And all these gadgets are highly optimized and make full use of the freedom that we have over the layout of the circuit. We also have some great examples from other projects, such as the ZK EVM Community Edition, and they've been able to express the EVM's opcodes using PLONKish arithmetisation. And they've also been able to build up a complex structure of interdependent circuits, making use of the lookup argument. Yeah. And it's a really impressive effort. A lot of the issues and improvements that I mentioned came directly out of this effort. Some other projects that I know of include DarkFi. So this is a private blockchain that allows private coordination, something like that. I just took a look at their repo this morning, and I saw like our chips and our gadgets being used in their code, and it was really cool. Another project I know about is Orbis, which is a ZK rollup on Cardano. So they're using Halo 2 in like a Haskell-y way because it's Cardano. And it's very cool to see what they've built on top of just using Halo 2 as a backend. And that's all I have. If you have some project or use case that you're working on and you want to see if like we can build it, just come to our workshop in the afternoon or like talk to me at any time. Yeah, that's all I have. Thank you.
Cool. Thank you, Ying Tong. Any questions? Right.
One thing I'm curious about is when will the Halo 2 like libraries / APIs be, or I guess like what is the relative level of stability right now for developers outside, and about what do you see as the timeline?
Yeah, that's a good question. Right now we're in beta, and we want to do a point release soon. Timeline, okay. I'm gonna say the next few months. Yeah, we've also recently undergone a license change, so Halo 2 will be licensed under MIT Apache. Yeah, and that's gonna come with the point release as well. So we're working to stabilize our APIs for that release. Yeah.
Cool. I have a related question for someone in the audience. Hi, Chen. Does scroll tag have a solidity verifier for our fork of Halo 2?
Yeah, we're still working on like a version that can take the proof like generated by the Halo 2 and then just convert it to some verified smart contract using the Solidity. Like it will be like a working, trying to build like some compiler that can take that and then just directly output some verified contract. But like we can like keep like update on that and then give out some news like once we have something. Yeah.
I think that verifier, it's important to clarify, is for like KZG commitments, right? Whereas Zcash Halo 2, like Barry mentioned, there's the arithmetisation and there's polynomial commitment. Zcash Halo 2 uses the inner product argument, not KZG. Yeah, and it uses like pasta curves, not BN254.
So, coming out from the discussions that we had yesterday related to Ketchak, I was wondering if, not only for Ketchak, but maybe in the future for also other cases and like complex circuits that are really hard to optimize for like this kind of constraint language, how do you see the future of writing custom layouters to further optimize your circuits? Do you think that that will be kind of the way to go for some kind of circuits, or how do you envision that?
Yeah, that's a great question. I do envision the future as being like a layouter-centric future. So I think we should move developers' customization efforts to the layouter level, the layouter strategy. Yeah, and if we can define the layouter strategy well enough, we shouldn't have to think about the minute details of every constraint. Yeah, we should be able to just concern ourselves with the configuration based on like the efficiency we want, the limitations we have, and concern ourselves with the business logic. Pick a layouter strategy that we like, and then not worry about other things. Yeah.
Any other questions?
How worried are you about security, and do you have any tooling to help with that?
We are concerned about security, that's for sure. So the Orchard action circuit was audited independently by QEdit. But I think even after the audit, we found several bugs on our own. And auditing ZK circuits is not easy. So I think there are a few things that could help with that. First of all, if we move the complexity to the layouter and we keep the expression or the business logic level human readable, firstly, I think that would help a lot. But yeah, secondly, I think coming together with other implementers to figure out like common gotchas and pitfalls and common things that we miss out, that would also help. And yeah, with regards to tooling, there is no formal or mechanized proving that I know of for zero-knowledge circuits. I think there's a session today about it. Yeah, so I would be interested to find out more as well.
Cool. Anybody else? Okay. Thank you, Ying Tong.